with the things what I have discussed in the morning session, and where in the morning session it is being clearly discussed related to the microwave. Let have a brief discussion, then I'll be continuing with enough waveguides. As we have discussed, what is enough microwave frequencies, where it is been given as in terms of frequency and in terms of wavelengths there. What is the frequency of microwave frequencies, and what is the frequency range of microwaves?
1 gigahertz to 300 gigahertz.
Yes, and fine. Good. So that's what I have said, that 1 gigahertz to 300 gigahertz. And in terms of frequency, it is being given as 30 centimeters to 1 centimeters. And where after that, we have seen that frequency range, and have explained about all the frequency range terms, and what are their band designations accordingly. And I also told that it is enough some scenario we have to write so that you can easily remember how to write the frequency ranges here. So that is 3 to 30, 30 to 300, 300 to 3000, once again 3 to 30, 30 to 300, 300 to 3000, so on. Up to certain extent, to the maximum extent, it has been easy to write these frequency ranges, and accordingly you have to remember all these frequency bands over there. And after that, you have bands, that is now L, S, C, X, and so on. So you have to remember this and their respective frequency bands here, 1 to 2, 2 to 4, 4 to 8. If you write once or twice, definitely I guarantee that you can easily remember these particular frequency ranges. And that's what we have discussed. And later on, we have discussed about all the applications, each and every point where practically it is being used. And accordingly, you have to remember all these applications of the microwave frequencies. And later on, we have discussed about the advantages and disadvantages. So these advantages and disadvantages also, the point wise have explained elaborately. And accordingly, you have to remember this. So in most of the cases, they have asked it for 2 marks or 3 marks. The applications of microwave frequencies or advantages they have asked. In other mean, they were asking about advantages or applications of waveguides. So either of these questions definitely they used to ask in 2 marks or 3 marks. So please do remember accordingly and start practicing and in writing that so that you can easily remember. And later on, our discussion has been moved to the transmission line, where the transmission lines, it is being told that it carries the information from one place to other place. So that's what the definition I have given as transmission lines. And as it has been discussed that the transmission line, like a two-wire transmission line as a telephone cable or a coaxial cable as a dish cable, and that's what use the transmission line at lower frequencies, which was discussed here. And we cannot use the same transmission line at higher frequencies, that is microwave frequencies. It has some problem. I'll be explaining what are the problems do we get across of using the same transmission line at microwaves, okay, and why we need to change the transmission line to which is suitable to work at microwave frequencies. In the next class, I'm going to discuss in detail regarding that, the basic reason why these transmission line cannot be used at microwave frequencies. So we have used a two-wire transmission line, and how the electric field and magnetic field it is been moving according to the right hand thumbs rule. So based upon that, the electric field and magnetic field has been represented with their directions. And you can observe that we have an electric field and magnetic field. They seems to be perpendicular to each other, and it is being called as transverse. Perpendicular in the sense transverse. Okay, so where the transverse electric and magnetic fields will process using the two-wire transmission line, and followed by an equivalent circuit. And we have given an expression for the calculating the impedance. Then later on, the inductance and capacitance can be calculated related to the two-wire transmission line. The same can be extended to the coaxial cable also. It is a type of transmission line which is used at normal frequencies, that is smaller frequencies. up to some kilohertz, up to some megahertz to extend, but gigahertz we cannot use. The coaxial cable cannot be preferred at gigahertz frequency transmission, where you can observe that all the electric field are perpendicular to the direction of current, where D is the cross-sectional area of the coaxial cable, and the inner conductor, small d, just I am mentioning over here, it means small d, where the current will be directly propagating. Based upon that, the electric field will be produced, and by using the right hand thumbs rule to the direction of propagation, so magnetic field, it is being produced during the circular, that is of the clockwise direction, as it has been represented over here. And you can observe that at each and every point, electric field and magnetic field are perpendicular to each other. That shows that both electric field and magnetic field are produced in coaxial cable. Means transverse electric and magnetic wave can be propagated in coaxial cable. Do remember this statement. I am repeating it. It's been very important. Okay, where transverse electromagnetic wave is propagating along the coaxial cable. So both electric field and magnetic field will be produced, and in turn, those two will be perpendicular to each other. Okay, so this is very important point. But whereas coming to the transmission lines at microwave frequencies, that is in a waveguides, okay, where there is no scope of existence of both the modes, both will not be perpendicular to each other, as TEM wave. You can I'll be writing it here. TEM wave can be able to propagate uh, in coaxial cable. So it is been possible in the case of coaxial cable, but this TEM wave is not possible in case of waveguides. So waveguides are the transmission lines which can be used at microwave frequencies. And as I told that these transmission lines cannot be used at microwave, so that we have an alternative waveguides, alternative transmission lines, which is suitable at microwaves is waveguides only. But waveguides will not support TEM wave. So do remember this one very important point. Why it is be not supported? We'll discuss in the next class only. Okay. So there are totally three modes which are possible. So one, it is transverse electric, it is been possible, and transverse magnetic mode, where electric field will be exactly perpendicular to the propagation of the wave. Here, magnetic field will be exactly perpendicular to the propagated wave. And whereas in third case, in TEM wave, both electric field and magnetic field are perpendicular to the direction of propagation. You can see that the wave is moving, the current is being moving, okay, in a particular direction. You can see that the wave is moving downwards. Okay, so you can see in the inner diameter, wave is moving opposite to where you look into the diagram. Okay, so as the direction is being straight line to the inner side, then electric field which is being produced. So this is being perpendicular to the inner current which is being flowing in that particular direction. And this electric field exactly perpendicular to this. So 90-degree phase shift here. So 90-degree angle will be there. So exactly electric field will be transverse to the direction of current. Apart from this, we have a magnetic field, and so this magnetic field is also perpendicular to the electric field, and in turn it has been exactly perpendicular to the direction of current which is flowing in this cable. Okay, hence it shows that TEM mode is propagating in coaxial cable, but whereas it does not take place in case of waveguides. So that elaboratory I'm going to explain tomorrow or in the next class. So wherever we have, when we have next class, I'm going to explain the basic reason why it has been not possible in case of waveguides. Now, after this, we have seen the calculation of inductance and capacitance over there. And with that, we have extended to the microstrip lines. So this microstrip lines, where it is nothing but a rectangular strip, as I've said, and here the wave propagations will be only in two directions, and in turn we have an electric field and magnetic field over here. Okay, so this is all the things we have discussed in the morning session, and now I'm going to extend the discussion towards the waveguide. as it is a transmission line which is used at microwave frequencies only. It's been very important. So today's class has been very important. So as maximum chances to get a 10 marks question in this topic, what I'm going to discuss today. Almost you may feel to bored at to some extent, but two important derivations I'm going to explain today, and those two are very, very important. And it has been so many times it has been asked. Definitely, I assure you that it is going to ask in external examinations. Okay, please do follow this clearly and join once it is being get terminated, so that I will be finishing this particular two derivations. Okay, so coming to the waveguide. So it's been not that much issue, and just it has been very clearly I'm showing. So waveguide, it has been, it can, I said that TEM is been not possible. So either TE is possible. So transverse electric waves are possible to propagate, and other case we have transverse magnetic waves are possible. So in this case, we are going to discuss that what is EX value, and so TE nothing but we have an EX, EY, HX and HY. So these are the fields which we are going to calculate for these two cases, and the two derivations nothing but one is related to calculate transverse electric waves, to calculate EX, EY, HX and HY, and another derivation we are going to calculate what are transfer magnetic mode equations. We are also EX, EY, HX and HY. So these four terms we are going to derive one, and remaining is similarly the following the same procedure. We can write the final expressions of EY, HX and HY. So those four terms of TM, four terms of TE, we are going to derive. Okay. We are going to derive for only one. The remaining is been similarly. You can just write the final expressions. Okay. Similarly, in the case of TM. So these are the two derivations we are going to work out today. So please be attentive, take the snapshots, and you can work out on paper, so that you be feeling easy. Okay. So please practice the basic things. So unless and until you will not be able to come out with the subject, and it's been very easy, I'm saying. Okay, nothing difficult in it. Okay, please listen and concentrate on my suggestion what I have given today. And those who are absentees also, please inform to your friends that it has been very easy to work out with these two derivations. Okay. Let me move to the waveguide. As I've said, it has been of waveguide is nothing but it guides the wave only. Why the name it is being given as waveguide in the sense? Am I fast, Andy? Can you able to understand the things?
Yes, sir.
If you feel any difficulty in understanding while I'm going to explain, please tell me something that, so accordingly you will go by that way.
Okay, sir.
Now a waveguide. So this waveguide is nothing but it guides the wave which is being passing through it. So that simple words it is being given the name as waveguide. So this is the transmission line only. So waveguide is a transmission line used at microwave frequencies. I told that some separate waveguide, separate transmission lines are designed to work out at microwave frequencies, and that is nothing but the waveguide. So waveguide is a separate transmission line which is being designed to work at microwave frequencies only. Okay. And how it is being designed? Okay, what is the shape of this waveguide? So there are different shapes we have. I am going to explain, show the diagrams of those waveguides also. So it is can be defined in a simple words that it is in a hollow metallic tube only. So where the wave can be propagated by reflecting from inner walls of the surface. Okay, inner walls of the surface, the wave is being propagating into the waveguide. Okay, there is nothing but in a water tap or a water pipe or in a plastic pipe where it is being used for passing the water into it, or during the electric wires also we will be making use of some pipes there. So that's nothing but hollow tubes. So that itself it is being called as a waveguide. Okay. So this is nothing but a waveguide, and I'm going to extend the advantages. Later on, we'll be moving out to the types of waveguides. And as I've said, we have an advantages of microwaves. Similarly, we have advantages of waveguides also. And it has been found that to design a waveguide, it's been very simple to design the waveguides only. Okay, the manufacturing process has been easier for designing the waveguide. The first advantage. Right. The second case, as the wave is totally penetrating into the waveguide, so it cannot, there is no possibility to escape in the atmosphere, so that it can able to handle the large amount of power, that is in terms of kilowatts. Okay, so that is enough an advantage. Next we have, as having the low power loss, as all the power it is being entered into the waveguide there, then the chances of wastage of the power will not be there. In case of waveguide, it's been very small losses. Okay, and the fourth one, it has been having low loss in the case of waves, also in the case of information also. Okay, and these two suggest that as the losses it has been found in coaxial cable will be more than compared to the waveguide ending, as there will be some insulating material loss, or there will be, in case of coaxial cable, the copper wire which is being used as an inner conductor, there might be some losses there, some damage it may occur inside it, so that it may be possible that there are some sort of losses may occur. But in the case of waveguides, there is no such losses only. Okay, so totally we'll get a complete information, whatever transmitted, it is been received over there at the other end. So this is an advantage of waveguide. And now coming to the types of waveguide, as I was saying that there are different types of waveguides we have. As if the shape of the waveguide is of rectangular shape, then it is been called as rectangular waveguide. And if the shape is of circular, then it is a circular waveguide. And if it is been elliptical in nature, it is of elliptical waveguide. Then we'll see single ridged and double ridged. I'll be showing the diagram. So these are the first basic two. As I've said, so the rectangular and the circular are very important waveguides, which is used very frequently. And among these two, the rectangular has been more preferred. And where you are having in a microwave engineering lab, tomorrow it might be. So there we are going to show how the waveguide it is being there, and different microwave components we are going to check out tomorrow according to the schedule, where the at the inner side you can see that it is nothing but inner side the wave will be propagated. All these four walls, outer walls, it has been of pure perfect conductors. Okay, the wave will be propagating in this particular path which is being provided. The wave will be guided here, and here also at the center. So from this is the center path where the wave will be keep on moving inside internally by reflecting from the inner walls. Okay, so this is according to the nature of the shape. It is being called as rectangular waveguide and circular waveguide. Okay, and next we have the elliptical waveguide and the single ridged waveguide. So we can see that, see, these are nothing but the 5 types of shape of the waveguides. You can take the screenshots, and so that you can write it in the running notes, so that you can easily understand the terms. And where you can see that as it is been elliptical in nature, so that it is being called as elliptical waveguide. Okay, based upon the shape. And here single rigid in the sense the shape of the waveguide will be of like this. Okay, and this is been of halo. So a halo inside it, where the wave will be propagating in this particular space, whatever it is being provided, and it is being called as single rigid. Only one side it is been of closed here. And you can see the next one diagram, it has been open at both the sides. So it's been open on both the sides, and it is being called as double ridged. So the shape itself, it shows that double ridged waveguide. But these are very rarely used, so that we are not going to concentrate much more on these types of waveguides. Okay, so we'll be concentrating either rectangular or circular. Okay, so now as I've said that one of the major disadvantage of the waveguide in the morning session, it has been very expensive only. The waveguide was expensive, and I have told the reason also why it is being more expensive. Why, and why the waveguide is being, the components has been expensive?
Inner walls are coated with gold. So.
Yes, and fine. If you could able to observe, fine and good. And where the inner walls have written the statement also, you could have used this one also. And I have told in the morning session, where the inner walls of these waveguide internally, what are the inner walls we have here? The inner walls which is being coated inside, where the wave will be reflecting and moving forward direction. So it is being coated with either gold or silver, so that it is been costlier. Okay, so this has been expensive, and that's the basic reason why it is been, the cost is been very high, and that is being considered as a major drawback. Now, as I've said, we'll be moving to the derivation. There are two derivations we have. First, we'll start with the transverse magnetic, and later on, I'll be explaining the transverse electric. And just please have a concentration, so that it will be easier for you to follow that. And meanwhile, if you have any doubt, you can ask me and you can approach me. And now, for this, I told that there are three modes which are possible generally, where TE and TM are passing through the are available in the case of waveguides, and TEM only in the case of free space, okay, or in the coaxial cable, in both the case. And so in the free space, suppose we want to propagate, then will TEM wave will be possible, and wave, electric field and magnetic field will be perpendicular. And apart from free space also, the wave can be possible. TEM mode of wave propagation is possible in coaxial cable. Okay, but there is no TEM in the case of waveguides. Please do remember these particular statements. Now, coming to the rectangular waveguide, where we have totally the shape of the waveguide is of rectangular in nature, so that it is being called as rectangular waveguide. Okay. Now I'll be explaining the basic concepts. You can see the diagram over here. The rectangular waveguide, as it is the rectangular waveguide, and it is being placed in the Cartesian coordinate system, because it is being rectangular in shape, so that we can analyze this particular rectangular waveguide using Cartesian coordinate system, where it makes use of X, Y, Z here. And here the broader dimension. So the dimension here of waveguide, it is being shown as an A, and this is now the B. So these are the dimensions of the waveguides, length and breadth, you can say. And this is permittivity and permeability. So we have a normal definition of permittivity and permeability. You might have come across this with enough EMTL. You are well known about EMTL, and you have, to some extent, it has been also extended in case of antennas also. We have the definitions and values of mu naught and epsilon naught. And epsilon naught, we have that permittivity. So epsilon is nothing but permittivity. It is nothing but a thing that is some material. So material will have some value, and based upon that, suppose if you want to penetrate a EM wave into the material, how much it is penetrating into it, it has been recorded with some value only. So that value is nothing but permittivity of that particular value. We'll be having some 2.2, 2.4, 1.8, 4.4, some permittivity values of the material. Each and every material will have some permittivity value. It shows that, so that much extent the wave is penetrating. Think that it is some material. Okay, so it has been some material. The wave, how much it is been, once EM wave is made to propagate through this material, then how much it is able to penetrate into the material, it is been given with some reading. So that is nothing but permittivity. And same, if permeability also the same only. How much the magnetic wave is been penetrating into the material, and it is being given with certain value. So that is being called as permeability. So permeability will be used for magnetic field equations, and permittivity will be used for electric field terms. Okay. And let us now discuss how to find the field components of this rectangular waveguide. Okay. So for that, I'm going to use some boundary conditions, where you can see that I'll be, it is been analyzed with some boundary conditions, where these boundary conditions, it is being shown that here X is equal to 0, and this is nothing but X equal to 0. And here X is equal to B. here x is equal to b here, and here the x will be equal to 0 here. And you can see that at x equal to 0 and sorry, the x equal to 0 and x equal to a, it is y, and sorry, it is, as it has been moving in this case, it will be along the y direction. So y will be equal to 0, and this is nothing but y. So it is been y direction, and along the vertical I am choosing here x is a horizontal. So as y is being moving from y equal to 0 to y equal to b, so electric field, so as we are saying that the field will be moving along this direction. So it is been shown that Ez value and Ex will be equal to 0, as the field will be Ey will be moving only. So Ey will be producing here. So Ey will be entering. It will be along the vertical direction. Ey will be entering inside. So it will be of like this and almost. So where I am going to explain that how Ey will be penetrating into the waveguide. So this is the signal. If you say that it has been at different phases, so this is the wave. You can see that I'll be changing the color here, so you can approximate that. So this is the wave. So positive peak and negative peak. This is the wave. It has been entering inside. Okay, with this vertical in nature. Okay, so that Ey will be existing here. So the field will be exactly vertical. Ey will be vertical, and so that it is been entering in inside, and whereas Ex and Ez will be equal to 0. So that this term will be equal to 0 here. And coming to the case of x case, where x equal to 0 here, and in this case here, and x is equal to a here. So x is equal to 0 and x is equal to a here in this direction. And you can see that Ex values here, Ex will be present, and the Ey and Ez will be absent here. So that the wave will be entering in this particular direction. Okay, so this is how the wave will be moving inside along this electrical waveform. See, this is nothing but it's been moving like this inside. Okay, we're maintaining the Ex value. Ex will be there, and no Ey and Ez will not be there. Okay, so this is how the wave will be entering into inside. I'll be showing how it is been moving out with some animations. I'll be doing that so that it will be very much clear for you. And now that with these approximations, I'm going to derive the expression for transverse magnetic mode. What are the values of Ex, Ey, and Ez, Hx, Hy, and what are the values of TE mode, Ex, Ey, Hx, and Hy. Okay. Now, let us first extend within of transverse magnetic. In the case of transverse magnetic, we have seen that the magnetic field Hz will be equal to 0 along the propagation of the wave, and only Hy and Hx will be possible. Okay, so that we are going to derive. To derive that, we are making use of this Helmholtz equation. So I'm going to use a Helmholtz equation. From that Helmholtz equation, it is been clearly written that so the x, y, z coordinates. So in terms of partial differentiations, it is being expressed as dou square by dou x square, dou square by dou y square plus kc square is some constant term, and with respect to Ez equal to 0. So Hz equal to 0 there. Now for Tm, Ez we are using. For while calculating TE mode, Hz we have to use here. Only that replica of whatever I'm going to explain now, the replica, it should be used for TE. Now, it is a function of both x and y. You can see here, it is being written in terms of x and y here, x of x and y of y here. Here it is being small x and capital X. X is a function of small x and capital Y is a function of small y here. And replacing the value of Ez in terms of x and y in the second equation. So that's what it has been done. So Ez, it is been replaced with those two x and y values. Now, once it is been multiplied here by differentiating this, the partial differentiation is being converted into the differentiation, standard differentiation. And here it is been multiplied. So x differentiated with x, it will be equal to 1, and y term it will be there, so that y it is been written in the first one. And similarly, it is been, we have only the x component with the derivative of y, and this ky it is been multiplied as it is, and this is another term. So there are totally 3 terms which are been possible, and which is shown in equation 3. Now with this, we have to simplify this. Let me explain how it is being simplified. Now dividing the equation 3. So this equation 3 we have, it is being divided with x, y here. So once it is being divided with capital X and capital Y, you can see here. So x and y, it is being divided. So then this y and this y will get cancelled. The remaining term 1 by x will be there here. And if I divide this with x and y here, and y, x and x will be cancelled out here. 1 by y is the term left out. And here if we divide with x and y here, we know that these two are same. This x of x is x, and this x will cancel out. This y and this y will be cancelled out. And we have only kc term. So that's what equation 4, this term, this is being given as same 1 by x, d square by d square, and here 1 by y term, and there is no term of x and y here. Both gets cancelled over there. Now we have to calculate the values, where kc is a function of x and y. So it is being represented as kx square plus ky square. We can also represent this kc square by kx square plus ky square. Okay. And with this, as it is being shown that by using separation of variables, please don't lose your attention and please have a patience. It's been very easy, and please make a note of it and practice it. Definitely you will get this question. And here all the x terms are separated and all the y terms are separated. So this term with the x is being taken out, and this term with y is been, all the k x values and y values are separated. And this is been simplified and expressed in terms of by using separation of variables. Okay, so that by expressing that, we have to calculate some constant values. I'm going to explain how to calculate those constant values. We can see here the above values here by using the differential equations separately to solve the equations there. And to solve this particular equation, so this is being written here. So this is the term. After writing the simplification of the terms, it is being written of this form, and dy by d square, it is being written by y is equal to in this particular way. And all the y terms will be there here, and c and d are constants, whereas here a and b are constant with all the x terms here. And we have to calculate the values of a and b. To calculate that, we have to apply the boundary conditions. So these are the boundary conditions I have explained initially. So before starting of derivation, I have explained this boundary conditions. So Ez will be equal to 0 when x will be equal to 0. We have to substitute. So substitute now. Now Ex x will be 0. If x will be 0 here, then totally this term will be equal to 0. We do not have this term. And when x equal to 0 here, cos 0 is 1. So when cos 0, we have a here. A plus 0 we have. And similarly, substitute here. We have, when we multiply these two, we have written x into y, because both are in single expression. We have to calculate x into y, so which is also equal to xz, and xy is also equal to xz. We have first analyzed. I'll be showing it once again. As I have told that Ez, it is being taken as the functions of x and y there, and where I'm approximating it once again here. You can see that. You can see the first initially where Ez. So this is the Ez is a function of x and y. Okay. So that x into y, once again it gives Ez. So that I am taking the same thing here. So x and y here. So this shows that x into y is nothing but equal to Ez here. Now substituting the terms here. So this term we have seen that this will be equal to 0, sine 0 as x equal to 0 there. This term will be 0. And here we have, here also we have, as we do not have the term here, let it be, we are not bothering about here. So this will be term 0 here. This a plus 0 will be equal to 0 here. Xy or Ez is equal to 0 here. So that a plus 0 is once again equal to 0 here. So that we have got a equal to 0 here. That's what I have written here. If we take the first term here, so where Ez will be equal to the first term, to calculate the value of AB, I'm using the first term here. As x will be equal to 0, this term will be totally 0, and we have left out as cos 0 equal to 1. Then a plus 0 will be equal to 0 here, so that a will be equal to 0. Similarly, apply the second boundary condition as Ez equal to 0, then y equal to 0, then substitute in this case. Then we get sine 0 here. So sine 0 will get here, sine 0 equal to 0. Then totally d will be equal to 0, and c into cos 0 is 1. So c plus 0, which is equal to 0, is nothing but once again c is equal to 0. So we have got the values of a and c. We need to substitute here, and we have to replace the values of kx and ky, and that can be done in the next step. You can see here, once the values of a and zeros are replaced in equation 4, so we'll get, you can see here, value of a and value of c is being made it as a 0. You can see here. So this term will not be 0. So this is being will not here. So this a will be equal to 0 here, and here the d will be c will be equal to 0. We have seen these two values is 0. Only the left out equation will be b sin kx into x plus d sin ky into y. Okay. So we are using these two equations we are using now. Okay. So now in terms of b and d, when we multiply b into d, and we have one constant amplitude term which is being given as b into d is being taken as b minimum, b mn, it is being called as m and n. These are the modes representation. I'll be giving clarity regarding this mn. So if the class get disconnected, please join, and one more small derivation I'm going to do. With that, I'll be winding up the class. And then the as ex equal to 0 when x is equal to a. When we take x equal to a here, then ex is will be equal to 0 there, because kx sin 0 is 0. This total term will be equal to 0, and ez will be equal to 0. So that substituting that, kx into a will be m pi. In terms of sine inverse of 0 is nothing but m pi here. Then k, if you take here, kx value will be equal to m pi by a, and ky value will be n pi by b. So replacing that, we'll get this standard equation.